Okay. Good morning, everyone. My name is Chao Long Yang. I'm a professor of industrial management and also the Smart Manufacturing Technology Institute. I'm the director. Today, my topic is computer vision, human action recognition, particularly in manufacturing. Okay. Here's my little bit short background. Basically, recent year I working on the big data analytics and also the artificial intelligence application. Today's talk is very focused on the human action recognition. This is a very particular area for the, I think it's in computer science area for the human body motion recognition. Okay. All right, so here's before I go to a little bit detail for this talk, I want to kind of have some interaction with you. My work for this talk is human workers action recognition. So you might have a question, why I need to know human workers action recognition? When I say action is the task is working on. So I have a question, why we want to know? Why we want to know the human worker? Do you have any comments? To know why it's doing. Yeah, but you can consider in a factory, that's about worker working. So here's one of the assumptions I want to make sure everybody understands. If there's no worker, this technology is useless, right? But a lot of times when we see in the manufacturing side, we still see the human worker doing something. And it's not robot, by robot, it's by human. So the one key question is, why we still need a human worker? Maybe you will see, okay, human worker labor is cheaper maybe, but maybe my answer is wrong, it's not that way. Because humans can and humans' intelligence is still very useful, maybe I would say that way. You can think about when you want to open, let's say, here's my cell phone, and you see that's a cover. You can ask a robot to open the cover. It's a little bit tricky. I want to demo that. I want to open it. Right? So I have to know, I need to push this button. I need to think. And you see it click, some sound, and you take it off. I don't want to drop this stuff. So think about it, you want to use a robot to do this job. You got to do it all the work. A human, this is a simple, I demonstrate it open. So that's why, particularly in manufacturing side, a lot of we still need a human to do some assembly work and maybe some tedious, of assembly task. Okay, so that's the first thing I want you to know. So if you want to know, if you know that's still working on manufacturing side, the key question is why we want to know what a human doing. Usually common answer is we still want to make sure that human doing something right, okay? In terms of quality, in terms of the SOP, the standard operations are correct. Also, we want to make sure that human can finish something on time, right? So we have some timing issues, particularly for production line, where some worker want to allocate human to different station and want to make sure everything is more efficiently, okay? So that's, we need to study human. But there is some difficulty when we apply this technology in manufacturing side. I will probably talk about it. But here is one thing. If you want to do online detect, then you have some issues you want to consider the computation cost, right? And second is, we also want to study the action and action between. So when I say action, you can assume that action is considered one of the tasks. For example, I want to open a cover of something, it's A. and I want to install something inside, is B. Then that's considered two different tasks or two different actions. Okay, so understanding the transition between these actions is quite important. Why? Because that means it's a certain time between two actions, right? And that is a particular time for preparation. Preparation means, let's say, I want to take this drink, coffee to my mouth, right? And that's supposedly one action. Then, if it's a production line, I want to make sure the coffee already put it on the table, right? So I can just simply do drinking, right? Think about that preparation, all right? So there's something. And today, this talk, I will probably focus on first two, and I think we might not have enough time to talk about a section. But here, I will probably say, when we study the human action recognition, sometimes the human will do something unexpected. When I say unexpected, it's okay, the worker is supposed to do A, B, C, D, but sometimes they will do something else. For example, scratch their hair, they put their finger in the, I don't know, and here, they want to take a cell phone out, they will speak on something, do something else. And that something else can be recorded by computer vision system, but I want to recognize it as a section or not. All right. So here's one. This is my major work we work on. We apply one of AI model. It's called spatial temporal graph convolution network. Basically, it is one of deep learning model. Okay, I will talk about it a little bit later. And we do the human action recognition and transition prediction. Okay. So let's quickly talk about the background. All right. So I want to show you a video, but this video is 2020 in BMW in Germany. It's a manufacturing site. And there's a worker working with a robot together. Usually we call this collaboration, right? Human-robot collaboration work. And maybe we can you help me to click the video to see? Okay. Yeah, I want to explain the video. So as you can see on the screen, there's a worker doing something. And robot is handling the gear set. And gear set is a bit heavy, right? So you're going to ask a human to do it, it's a bit heavy. So you put a gear set, but you can see the gears over there, and obviously it's in one part of the transmission. And want to assemble it. And human actually doing something else to support, but at the same time, do you see, you try to do some vibration and make sure the gear can be fit. Then the human doing something else to maybe take something else and do something else. If you human doing this way, and the robot can do, of course, but the human just very near to the robot, and human do one thing, robot do something. Here I want to demonstrate, hey, this is in touch with the hand, right? But don't worry, because the robot would know, they will stop the position, okay? So here's a very typical example I will now share with you. It's a human-robot collaboration. But at this application, and certainly the human working on something simultaneously with the robot, right? And robot also need to know what human doing. So that's why we need to understand what the human doing on certain position. Okay, all right. So here is an example. Can you go to another slide? Sorry. Okay. So here's a real world worker operation. Obviously, you see this human worker is doing some assembly, right? First, we take something from a rack and want to put them together. And it got a screwdriver, electrical, doing those things, okay? And when we say it's computer vision, is that we actually put a camera in front of it, right? And you see some of a point on his finger because we use a certain kind of technology to detect it's a finger point. And we use those information to understand what is a human worker doing. So if you really want to know he's doing it, you will say, hey, he's doing something assembly, right? But in industrial engineering point of view, no, he's just, of course he's doing an assembly, but he's doing several different tasks. As you can see, he do a screwdriver, there's one task. Another way is to put a cover on it. Maybe you tell him, take a cover, and maybe sometimes you put a label on it. So if you want to know that the computer vision system to understand what the human doing, that is the major work we are trying to do. Okay. For the past 4 or 5 years, we continue working on this area. It's very challenging because computer science area for the computer vision human action recognition is particularly one of the special domain. This domain is want to recognize what's a human doing, but their original problem is not that difficult. Let me explain it to you. For example, I give a video clip. It's something play tennis. Some people, badminton, table tennis, basketball, soccer. So we let the computer to read the video, maybe just 1 or 2 seconds, and recognize it. Hey, what kind of sport it is? Hey, yeah, this is human action recognition. And also, there are some areas called human interaction recognition. Human interaction recognition is about, for example, I'm shaking hands with you. So that recognizes I'm shaking hands. Or maybe I drink coffee, maybe we're talking. Maybe I hear you. It's an interaction. There are a lot of interaction. Maybe some people kiss somebody. Yes. So it's recognizing interaction. So it is a certain area in computer science that people actually doing something using computer vision to detect. And also there's some area called anomaly detection. It's very relevant. For example, I want to detect if there's a terrorism attack, if something weird, suspicious moment, maybe you can hurt the population, right? It's something. So, for example, some people put a surveillance system in the MRT system, subway system, highway somewhere to understand if there's a human or on the wall side to see what happened. But our work is a little bit different. We are not really worried about anomaly detection, but we are focused on the worker. They have been those workers who are asked to do something based on certain procedure. We call those procedures called SOP, standard of the operation, right? The worker have been asked, hey, do this first, then screw driving on this certain nut, and put some cover on it, and turn back and put a label on the do something. Having asked, those SOP have a certain frequency, a certain sequence. Okay. So human need to follow. I want to recognize it. Okay. But we need to recognize it real time. And also we need to recognize if it's something in between. Why we want to study the transition? Because we want to know how fast we can prepare. For example, you can see, I'm putting on video, if you are walking, then if somebody, maybe a robot, want to give me some parts on hand, that we need to consider the transition point. I want to make another example. Do you have a chance to watch the video about the doctor surgery room? Usually, that are doing something surgery test, right? When you have open, what you ask is ask the nurse nearby to maybe put in some of the tool. And another example, you ever have a chance to go to a dentist? And you're sitting there, your dentist is focus on your mouth, right? But there's another guy working on, there's a collaboration, right? He's trying to sell something out from your mouth, right? That's a collaboration. So those collaboration, if you think about collaboration work, that there are certain times in transition you need to prepare. For example, when the doctor needs to put a mouse in, and of course, you have to watch it and make sure what I can assist the dentist do something. So you need to earn those transition time. So this research focus on, I want to understand what a human actually, I also want to recognize when is the transition time, and that's a major work I want to do. So we have two actions. Actually, this work as one of our research will kind of create a model separately, but it's not simultaneous to detect. So we want to create a model, put them together. So idea is we create one system for human action recognition, but also another system to detect if it is a transition or not in certain time. All right, so maybe it's a little bit like a literature review. Actually, AR is one of the particular term in computer science. But here I want to put a little bit detail that some people call the human action representation and also characterization. Obviously, characterization is what I just said. I want to know you are doing A, you are doing B, you are doing C at a certain time. But representation is something like what you see on the human. There are some of the technology can detect the human bodies, skeletons, and also the information as for representation. Okay. This is a literature review. I think I talk about this several times. It we call before and after deep learning. Before deep learning, usually we try to capture the human body's characteristic to understand the human's particular point, eyes, or body, hands. But after deep learning, coming up, there are new models that can use a little bit more deep and network to understand the human body textures. So it will be relatively breakthrough. So since 2013, a lot of CNN, LSTM model coming out to detect the human body. And also there's another trend that's focused on the skeleton. And it's very focused on using we call the pulse estimation tool to recognize the human body's eyes, or body, or skeleton. So there are actually two trends. And right now, skeleton way, and this way is called image way. It's very popular. Image is very focused on RGB images. That usually your image frame as an input for the model to detect what you're doing. But skeleton way is we use the image to extract the skeleton first, and use the skeleton put it into the model. So there are two ways to do this, measuring. Okay. I want to probably skip those literature review. This is relatively old, but still a major breakthrough for the image-based or skeleton-based. One of the idea is we use the image, use the texture of the image, and you can use some computer vision technique to extract those ROI, region of an interesting point, and focus on the face or focus on body and to do the recognition. But skeleton, having extracted a skeleton, you can detect the skeleton already, so we can put it into model. So the model design a little bit different. I mean, for AI model, right? So there are some of action recognition, representation. The way we did, we used to use one of the techniques called open pulse. I use all open source, open pulse. But right now, I think more popular way is to use a media file, and you can detect hands and also body. It's developed by Google, so it's a kind of open source. We use it to extract human body skeleton information. All right, and of course, for a classification, there are a lot of different models coming out, CNN-based, LSTM-based, and CNN plus LSTM-based, and also GCN. The way we did is very focused on GCN. It's called Graph Convolution Network. It's a little bit different. I will introduce it a little bit. CNN versus GCN. It's a structural matrix basis versus graph basis. Different idea. Okay. So methodology. Our research framework actually coming years we follow a certain way. Of course, we get a video. Recently, we developed one kind of a technique. Just record very short video, like 1 hour. So we were able to train the model already. Because when we apply this system, you probably see later, we apply this system on site in working with a company in Taiwan. And the company that was certainly don't want us to, store so many video and do a model training. So we kind of develop a very short time video training. But based on our study, I think 1 or 2 hours is enough because within the 1 hour, a human would do the SOP maybe multiple times, maybe 20 times already, good enough. So we take the action, model representation is when we extract the skeleton, right? So get a skeleton, we do a data labeling, and data labeling follow the SOP. Because these people are supposed to do A, B, C, D, and we do the labeling by friend. I guess, I'm not sure, do you know computer vision? We usually talk about FPS, right? Every single second, how many image frame we can capture. The number is larger, as the more resolution is higher, right? So it's a bit faster. So suppose it's a 30 FPS, that means in 1 second we have 30 frames coming up, but we are putting every single label on is a frame. Okay. So once we did that, then we can extract skeletons, join and label, and then we do the data processing. And here is a representation model from MediaPi. Of course, there are more and more new different pulse estimation model coming out. But for MediaPi, this kind of system, you can create so many different data points, and it will come with a different number. It's one hand, but of course, we have two hands. So you can correct those data points in 3D and 2D basis coordinate, image-based, right? Coordinate, you capture data. And that data is how we know what's a human doing, all right? So here's this example. The data labeling is very typical. I asked my student working on this project, what he did is he put your PC on the table and try to do the assembly. So we want to assemble CPU, fans, right? CPU comes with the fans, and so memory chips to put them together. This assembly work. So we record it. So here is the example, A and B and C. But you can see that there's multiple frames inside for each particular action. So at the same time, we also want to recognize the in between. Think about what happened. If you in front of my table is a model board. Okay, let's say I want to put a CPU on there. Click, done. And then my hand try to capture another thing to put in, right? And that is certain transition time. It's not doing the CPU assembly. It's not also the assembly of the fans. But it's different between. During the transition time, usually human doing movement, right? That movement is take something, and that transition is very important. You want to do the human-robot collaboration because if you detect this time, we can predict this time. Then human-robot can maybe, hey, that's your friend. Then we take it, something. Okay, so we put in between. And we want to recognize this correctly and also want to know this transition is on the right time, okay? All right, also after that, so here just an example that A, B, C, D action come with different time, right? Different action might take different time. But in my system, we all consider by using number of frames. So this action, how many frames? How many frames? It's not second because it's so fast. Human is very fast, couple seconds. But we do it in frames. So when the model want to recognize what is doing, what's the next, what is it doing others, okay? So in a real-time inference, we are unsure what is a start or end. So we keep tracking every single frame and try to calculate the probability for each individual frame. And then we can certainly use the probability-based model, this kind of fuzzy model to detect what is in transition. Okay. Maybe you already finished, right? Your image is what you already put into, finish it, then start to do something else. Your probability for doing this is lower, but your probability doing others is higher. So you can use the system based on probability basis. We can calculate it. Okay. All right. So here just a kind of example for you to understand. So since we're doing continually, we keep tracking, right? And we collect certain windows of the image and use it, not only one image to train the model, no. This system we try to create is we collect multiple images at the same time and put it into model. You can consider a very short video and put it in the model and you can handle. So the window is moving. So if you see at a certain time, your probability actually changes, then we can detect and say what is the people actually doing, right? So once we did this, we trained the model, We also consider probability filter together. And filter can extreme. Basically, filter is a kind of filter we want to use it to filter the output of the model. Then we can make the system more stable. Okay, you can consider it. Basically, calculate the probability for each action. And once we've done this, and put it to, we can determine that, well, what this is particular friend, what is an actually human doing. So, and the model we use is the STGCN. This model original published paper in 2018. So at that time, it's kind of breakthrough. Usually before the GCN, people use a CNN model, image-based CNN model. But this model turned out to be very efficient. I think the very early time we implement the system and also made some modification, particularly for our work. Originally, this paper is focused on using SDG to detect that sport, tennis of different types. So the input is a short video, but we changed the model to be like a standing window basis and go to every single work of a human and try to detect probability base. That's what we're trying to do. Okay. So the main idea of STGC is just using a skeleton and create a kind of a join and joins graph, and use the join and join graph information as a model for training. I think that's the major differences. So you can see that inside the system, spatial temporal is not only consider the joint and also consider the age and by different time. So assume your arm is moving, right? So you see your joint may not change here, but your joint changes. So you can consider the correlation between the joint and also the based on time. Right? So you kind of record the information on that and train your model to recognize it because it is all image come with a frame. So you can see when I get into the sliding window moving, the window comes with the individual frame stable and also the joint information and age. Okay. And compared with the CNN, CNN is a very well structured matrix basis, right? Because it's a pixel, right? Pixel basis, right? You learn this in AI courses, you suppose you understand how they do the convolution. But for GCN way basis is a GCN systems. But after all, they will convert it all into the vector basis to work on this. All right. You might interested in go a little bit of detail. So when we get a website in window, so very early time we record something, then we start to move the window. So we put in the model, and model can kind of give us a probability basis so fast. So we try to know, okay, it's doing this thing. Okay. All right, so since we have probability filters, so he just give you an example. So once we get, assuming we have only ABC, we can calculate probability and kind of to recognize which action is doing. The higher and higher, right? Higher, and start to change. Okay. This is for action recognition. Okay. Right? And since our system simultaneously handle it, so we have trained the SDGCN, and in the end, we combine with the transition information, put it together by using the SG Booster. It's another classification model to recognize it, the human's work, the action, and also what's the transition. So the transition is calculated by the, it is a bit detailed, but you can consider, right now we all have a probability for A, B, C, D, individual frame. But we also combine those information with the feature is a transition. So we want to consider not only action, right? We want to say, hey, this is a transition, this is a transition. And transition movement is a little bit different. Usually human, in our case, is their hand just moving somewhere to take something, right? So we can recognize it. Okay. We can recognize it. If we can recognize it, we want to predict it. And it's about to do it. Although this hand is still on the motherboard, right? You haven't do it. But since we want to detect the time, it's finished, but it's ready to move on to go somewhere, and that is transition movement coming out. So we use the transition calculation, this one, mean the information, and put them together. Okay. So here is just an example. We have 1, 2, 3, 7 different action, right? And this is time, right? This is by frame. We use a frame as our basis. And the red part is a transition. You can see the transition is a little different. For some work, that transition is longer, some work is very short. So we want to recognize it. So our models of verification is to make sure, one, are we able to detect those action on the right frame? Second, are we able to detect the transition time on the right time? And that is what we're trying to do. So the model will look like this. Here is actually it's an attribute doing, but not human doing, but just give an example. We can find out that certain time is a transition, have a high probability. So there's a transition, we can recognize it. Okay. All right, so here's some result. For some time I'm working with Professor Lee, the team working on this for a long time, and then doing assembly, recording, and I think it's in our industrial proposal center. So we have multiple different actions designed. And so here is a data set, so you can see how we collect several different training data, and we try to train our model. But of course, it's I just want, some of my students at that time, they assemble multiple computers just because they want to make a recording. And we not only ask one student, we ask multiple different students to do it, because different people might do exactly the same thing, but differently, right? Some people call this one, some call this one, but we still need to recognize the variation, okay? So here's a multiple transition work that we detect. Basically, I think we published this paper already, okay? So that's what we're trying to study the data. I think it's exactly the same. And we'll compare with another different GCM model, because this work, GCM is very dominant, so we compare with different sliding window strategy for other papers. And we want to see if our transition basis idea works or not. Okay. So here's the result. I think pretty fine. Yeah, but obviously this sliding window original GCM is not working very well. And our method is quite nice, okay. But maybe not dominant, but our running time is much faster. So that is for us, for training, that's pretty good. Okay. So accuracy fine, and here just an example. You can see the probability based filter out. You can see different color come with a different work, right? Text. Okay. So you see at a certain time is pretty much we are sure it's assembly CPU, right? This is CPU blue, but after a certain time it was going down, another one go out, right? So here's the transition we actually can detect. Yeah, but we put another label on it, so we'll recognize that this is a particular transition work. Okay. So here's a result. We can probably see that. Okay. But one assumption is still there, right? The people was asking to do SOP, right? So we can recognize this SOP should be very fine, no problem. Right? So we can detect the label, we can calculate the frame, we can understand the time. So after rule base, we compare with the rule bases, the different models, so we can probably maintain like 90%, probably 90% accuracy, frame basis. For instance, 90 is good enough, I will tell you. The frame basis, human eye 30 frames per second. Human can really detect the differences between, but we still recording. Okay. So we apply this in a real world company. So put it into here is just an example. I'm sorry it's in Chinese, but basically it's a we want to predict what it's doing. We calculate the time. So right now, this kind of system you put into, we exactly know this person, how much time he spent on certain task. Human has a different variation, right? Different human might have to do different time. So the company can use this calculated time to do the line balancing. Production line balancing is one of the particular term in industrial engineering. They focus on how we allocate the right person to the right station and to make sure that's smooth. Because you can consider multiple stations connect together. This is what we make sure everybody doing the same time, right? So that is the important work. And right now, this technology used to just record the time, but also recognize it. If you're not, how's human doing? They put the clock, they put the watch to time your every single action, but that's not obviously too much, not really accurate. And right now the system is really accurate for calculating, detect the time when people are working. All right, so here's some conclusion. Basically, this is a continual work we did for a long time and try to do the human action recognition. Ideas of doing this not only record the time, monitor the human, no, also can work with the robot and do a human-robot collaboration. And here is our result and some of future work. We're still working on it. And one of major future work is we want to detect exception work. When human doing SOP, but at the same time you take off the jacket and also do something else. Are we able to detect it? If we are able to detect it, we can calculate time. Perfect. Okay. All right, I think that's basically all my work. All right, any question? Question?
How about the all partners from USC?
Yes,
Any
of course.
comments from Professor Chen?
Yes.
So, Professor Yang, very interesting talk. I have a question. So, you showed this on real test results. So those actions are recognized by the algorithm, or you have to specify which action you are interested in. So you train them before using this recording of the video.
Very, very good question. We actually work with a company. The company asked us to install the camera in a series of stations. But that company doing the assembly work, okay? And basically what they give us is they tell us this station the human need to do what kind of action. So you can see simultaneously the worker working. One station maybe 5 action, but next action station maybe different number of action. So that what they need to give us, there's SOP work. Okay. Then we use that information to do the labeling basically. Then train our model. So
still need some labeling.
Yeah. We still need to do some labeling, of course. But you follow those. But the good question is, I think this question correlates with one of the issues. The company asked us to record the action because they believe the humans work, especially when humans just standing there. The action may be we can find out the limited number of human act motion. Then once we collect those data sets, then we probably don't need to do the model training. But of course, there are some issue we need to discuss with because we want to make sure the environment. The environment also is one of concern because, for example, for some workers, they prefer to put their screwdriver somewhere. But if you put it another side, your motion actually changes, but they're doing exactly the same thing. So the company, after working with us, the company kind of tried to synchronize, to make sure that everybody's workstation is consistent. But I'm not sure it's a good idea now because supposedly it's a little bit affect human factor issues because of the station supposed to fit the human's need. So, but not really conversion. So it's kind of challenging still working.
Humans are not robots.
Yeah, human are not robots. Okay, I say, hey, that's a very funny work. Some of the tests is called putting a label. They want to put a label on it. Okay, but some people prefer to put on right hand side, but some people prefer to left hand side. Yeah, but for our recognition, it's totally different action. But the works are the same, so that kind of challenging. So if you are able to make this more flexible, is what we try to do is exactly what is working, but use a different pen. But it's also possible. But currently, labeling is one of the concerns we're still working. So we can only assume if it's a right-hand person, with our model probably no problem. But it's a left-hand person, the model probably will be trained. That's for sure. Okay. Thank you for your question. I'm
Thank
not
you.
sure, did I answer your question correctly? All right.
How about the classroom?
Yeah, any
Any
student
questions
here?
from the students?
Comments, question? Yeah, please. Yes.
And is it worth to the worst
It's okay. You can speak Chinese. I will do a translation.
就是假设他遇到不预期的情况，那是在全职选的时候比较糟糕，还是在就是他做动作的时候？
Oh, it's a good question. Yeah. The student question is if the human worker do something is exceptional, right? Right. So that transition what happened? Actually, transition we totally screw up. Why? Because exception work is if you are not able to detect the exception work, the whole system, as you know, deep learning model, you will still record it and put it into the system. It still recognize it and give you one of the answer from that 7. If you only have 7 label, right? So that's a problem. So I'm still, because of time, your question is supposed to be answered here because this research will focus on the exception work. And it's not supervised learning, it's unsupervised learning work. Unsupervised learning is we are not able to list all possible exception work. No problem, no, not impossible. So we just need to do, you can consider, the test we collect is already have some pattern. Beyond this pattern, we consider the exception. If that we can detect, then we are able to find a good transition. This work we we use a very simple YORO B7 to detect the human body space. Then it can help a lot to do the detect the exception work.
Do you try to classify exceptional actions?
Yeah, we try to.
Like picking the nose?
Yeah, that's so many.
Standing up?
Picking a nose, it also depends on they have a right hand. That's so tricky. So, but
Or touching your
glass, yeah,
touching your
scratch,
computer.
yeah.
So you try to classify those as well.
We try to, but we just realize that we cannot exhaustively list all the possible
Yeah.
exceptions.
Yeah.
So we create another models more like a unsupervised learning way to make sure it is beyond also something we already trained. So each exception. But if you have a chance, the next time I can present the work for essential work research. It's a little bit funny, interesting. I actually my students try to create the ideas of how many essential work the human can do. And they create so many, try to do the task for the work. Okay. All right, question?
I was wondering for localization, like, is there any future plans to combine two sensors together to create a 3D environment for better observing?
Yeah. When we work with a company, we actually get a lot of feedback. One of the feature is very uncertain. The company want this system is very lightweight. Now uses a very fancy computer. Okay, one without working on. And secondly, the company really want us because currently we put one camera for one person. Although the camera is not expensive, but they want to know if let's say I put a camera can record, maybe can see 3 person, we can simultaneously handle 3 person. And that is another issue we are handling. But that is possible, but it's a trial. You want to simultaneously handle this multiple person, they also mean you need a little bit more computation power. And you also need a lightweight. Okay, this is, this trial, that's, we're trying to optimize the work. Yeah. All right, I think, thank you everybody joining this section. I hope, since we are still working out with this with Professor Li, man, we hope maybe we have enough time coming up to show something else if you are interested. Okay.
So Professor Chen, thank you.
Yeah, thank you. So,
Great.
yeah, thank you.
Great. Thank you.
Thank you for joining us. Maybe we'll see you next time,
Yeah,
right?
see you next week.
Yeah. All right,
Bye.
thank you.
Okay, bye-bye.
Bye-bye. 谢谢同学。